This is the fourth Webtalk in the Mplus Webtalk series. It is a companion piece to a new paper by Tihomir Asparohov and me. The paper describes new statistical techniques as well as new Mplus language. A major feature concerns analysis of longitudinal data, often called panel data, using cross-lag modeling of two processes influencing each other. And this is the topic of this Webtalk. The Webtalk has two parts. Part 1 describes the analysis of continuous variables. Part 2 focuses on binary and ordinal categorical variables. The categorical case is a more complex topic, drawing on several different model types. A detailed description is given of how to analyze categorical variables using the popular RI-CLPM model. In both parts of Webtalk 4, many different Mplus scripts and data sets are presented, together with a discussion of the results. Turning to slide 2, this is the overview, and here we have the paper that I was referring to, which coins a new phrase, residual structural equation modeling, RSEM, which is a new feature in the new Mplus version 8.7. And it has special applications to panel data analysis. I'm going to start with talking through some basic multi-level and longitudinal concepts to get a framework within which we will discuss different kinds of panel data models. And then I'll introduce the new residual language in Mplus and show how that can be used in applications to depression and self-esteem using two different data sets. First, starting off with univariate analysis that I suggest that one does for each process before putting them together. And we can explore many of those models that we mentioned in bullet 3 for the univariate analysis already. And then we turn to the bivariate analysis and you take a close look at the cross-lag modeling. And as I mentioned, part 2 is a later Webtalk part. Slide 3 presents two very common models for cross-lag panel modeling, CLPM and the random intercept RI-CLPM version. At the top you have the classic CLPM model and at the bottom the RI-CLPM. And they look quite different and they have quite different implications in terms of interpretations and in terms of model fit. We're going to take a look at the details of these two models, but at this point let's just look at it from a general perspective. We see that the top model has the two variables y and z going forward in time, in this case 4 time points. And the relationships between the y's are called autoregressions, regressions on themselves over time. Whereas the cross-lag is y2 regressed on z1 and z2 regressed on y1. In contrast, the model at the bottom does not have direct relationships between the observed variables, the y boxes, or between the z boxes. Instead, relationships are between latent variables w, y, and wz underlying the observed y and z variables. So you have these autoregressions and these cross-lags. What we do here is to introduce a latent trait that we will also call the random intercept, one for y and one for z. These are latent variables that influence the outcome at all time points the same way with loadings 1 in both the IY and the IZ case. So that's a quite different formulation than the classic one at the top. So you have to carefully look at where the arrows go. Do they go between the observed variables or do they go between other variables, like these latent underlying variables? This is related to David Kenny and Zotra's 1995 model that was investigated further by Cole and others in 2005, the so-called trait state error model. And the model that we show here is actually the Hammacher et al. Model that she labeled RI-CLPM. The trait state error model actually is a little bit different as you note here in the drawing of the RI-CLPM, we have no residual arrows for the y, for the boxes of y or the boxes of z. We could have drawn them, but then they would have had the value 0. That is, there is no measurement error here in this formulation of the model. That makes the model easier to estimate while still fitting the data well. The TSE model, however, does include that measurement error, but has to do so under certain model restrictions. For instance, equality of the residual variances across time, or fixing the first one equal to the second and the last one equal to the one before that. That's a model that's been found to have a hard time converging in many data sets. Now, these two models have been further extended, or extensions of those models have been further discussed in Mike Cypher's overview article in Organizational Research Methods, and by Usami as well. And they talk about a general cross-lag model. Now, to understand those models a little bit better, we're going to take a look at some basic multi-level modeling concepts. We're going to take a look at multi-level regression with the random intercept. After all, these models involve regressions, both in the autoregressive part and in the cross-lag part. So consider for a moment individuals I clustered, or within clusters J, and we have the regression of Y on X with a intercept beta sub 0 that has a J subscript. So it is a random intercept. We could have a random slope as well, but at least in multi-level modeling, do you want to have a random intercept? So that's the level 2 equation, where the random intercept has a mean and a variance as the variance of U sub j. So that's a standard multi-level modeling situation. Now, this could be students within schools or classrooms, but we can also have time points t within individuals. So repeated measurements for a group of individuals. We're going to take a look at a special case of 4 time points. I'm going to describe it in 2 ways. On the left here, you have the 2-level long format analysis, where you have the regression of y on x with a slope beta. That's this beta up in equation 1. And you have a fill circle at the bottom of the y box, which says that we have, in Mplus notation, that we have a random intercept, and that becomes a continuous latent variable I on between level 2, describing variation across individuals, as opposed to variation across time. Now, we can describe that situation, that multi-level situation, also in a single level wide format fashion, which we have on the right. For t equals 4, we have 4 time points, so 4 y variables, 5 and 4 x variables, and they have the same slope in line with the picture on the left and the equation up here, and they have a random intercept with loadings 1 influencing all 4 time points. The loadings are 1 because we look at equation 1 here, and for all time points, or for all individuals within the cluster, we have the same beta 0. So it's a loading of 1. Now you can do this single level wide format translation of the 2-level model when you don't have too many cluster members in this case being the number of time points. And that's the situation that we're looking at here in terms of cross-lag panel modeling, a relatively small number of time points. Now, if you dig a little deeper, turn to slide 5 and take a look at centering, observed variable centering, and we're going to talk about latent variable centering as well. So observed variable centering has been described very well by Raudenbusch and Bragg's book, Hierarchical Linear Models. They have an excellent table 5.11 that I refer to quite a lot. So you're looking at time points t within individuals I. So you have this equation y, and you have that random intercept now. It varies across individuals in this case, but not across time point. And then you have a beta where you have centered the x variable. You have subtracted the mean for each individual from the x variable. You have centered it. Group mean centered it. And on the between level, the random intercept is described as beta 0, but also as a between level slope multiplying this same mean, group mean that you have in the top equation. So that's centering, which is suggested to be the appropriate action to more clearly understand the influence of x on y. You actually have two slope, a beta w within and a beta b between. And if you ignore that difference between them, you, as Raudenbusch and Bragg say, you get the uninterpretable blend. Now, if you look at this more carefully, though, what about y? Well, in a sense, we already do a centering of y as soon as we bring in the random intercept. You can bring that random intercept over to the left-hand side, then you have y sub it minus beta sub I. Beta sub 0I, I should say. That you could call yw within, which is equal to a between slope times, a within slope times the within variation. So when you have formulated a model with a random intercept, you have in effect centered the dependent variable. Here we also center the right-hand x variable. And notice the difference here. We have an observed centering of x. It's an observed mean. Whereas for y, we have a latent centering through the latent random intercept. So that is actually then a latent variable centered model that we talk about, or that many people talk about. Lütke and others talked about it. We talked about it in 2019. You have the references at the end of this PDF. And Ellen Hammacher and I talked about it also, the centering issue in the connection of panel data modeling relating to the debate about fixed versus random effects. What this model, the RICLPM model, does is latent variable centering of y and of x, in this case z, because you have this random intercept. So you center the variable, and then you look at the relationships between relationships among the within centered latent variables like this. Relationships on the between are relationships between the random intercepts and any observed individual level variable that doesn't vary across time, a time invariant covariate that influences those random intercepts. That would fall in the between level part of the model. All of this, of course, done in this picture, as its picture shows, in a single level wide format, which you can do as long as you don't have massive numbers of time points. So this is suitable for 2, 3, up to say maybe 50 time points, whereas when you go beyond that, you're really into intensive longitudinal data, which are better handled by time series analysis like DSEM or RDSEM in Mplus. Now turning to slide 6, this of course relates also to growth modeling with random intercept and slope. So staying with a 4 time point in case, we have here 4 time points, and we have a y outcome. X-axis is time, and we see that individuals vary in their starting point and they vary in their growth rate over time. Starting point then is the random intercept, this latent continuous variable, and the growth rate is the slope. And they both influence the outcomes over time. The I variable, of course, then is a between level variable if you want to think about it in multi-level terms. And on the within level, we have the variation across time. And here we could have time varying covariates if we wanted to. And one thing to think about here is the role of I is partly to explain the correlations among the y's over time, the intra-class correlation, so to speak. They correlate, according to this model as drawn, the variables correlate because of all of them being influenced by I and also by S. I would say, though, that the random intercept influence on the correlation across time is larger, typically, than the one of S, because the variation in the intercept is typically much larger than the variation in S. On slide 7, then, we continue these basic modeling concepts, and we're going to add autocorrelated residuals, which brings us closer back to the RI-CLPM model and other panel data models. So in statistics and in the repeated measurement situation or growth modeling situation, we have the classic paper by Laird and Ware in 1982 in Biometrics, who introduced random effects models. That is, random intercept, random slope. And then there was a follow-up article in the JASTA, Journal of the American Statistical Association, which added autoregressions among the residuals. So the residuals are regressed onto each other with the slope plus a random effect. And this is the so-called AR1 model. The residuals are autoregressed by lag 1. So t depends on t minus 1. You could have t minus 2 as well. That would be AR2. So in the special case of no trend, that is just a random intercept, no slope, but adding a first-order autoregression among the residuals, we have what I would call a RI-AR1 modeling. So you have the random intercept here influencing the variables. We don't have relationships between the observed variables directly, but we have these residuals at each time point, the epsilons, and they are regressed onto each other. So the residual epsilon 2 is regressed on epsilon 1, and it has a little residual in that residual regression. Residual for residuals. So this is how you would draw the a pretty standard statistical model for repeated measures with a random intercept and an autocorrelation across time. And we will recognize this as the univariate part of the RI-CLPM model. But first, we're going to take a look at some other models that have been used for panel data. On slide 8, we return to the statistical tradition of random effects modeling in line with Laird and Ware, with the addition of errors that have autoregressions among them. And we've simplified it to have a random intercept only model in this case. And I said that that is the univariate part of the RI-CLPM model, and we see that more clearly if we redraw the top model equivalently as the bottom model, where instead of the residuals not having any variable really here, we introduce a factor that's measured by the observed variable with loading 1 and error 0. That's exactly what a residual is, right? The epsilon is not pre-multiplied by any loading, and it is the only residual that affects the y. So drawing it in this way, it looks more like the univariate part of the RI-CLPM. We have the relationships among the latent variables down here, not among the observed y variable as in the classic CLPM, and that's the same situation as we have here, regressions among the residuals, not among the variables. Now here we've marked explicitly a measurement error of 0 here. There is also a way to do TSE error modeling, allowing measurement error. But again, as I mentioned before, you have to impose certain restrictions on the measurement errors. And it is a model that often has convergence problems. And again, we note that the classic CLPM does not include the random intercept and has regressions among the observed y variables. So quite different. Turning to slide 9, it's interesting to look at how the random intercept and the autoregressions impact the correlations across time. So we're looking at 10 different time points here, and 2 here means at time point 2, how high is the correlation with time point 1? And this is the case where the random intercept variance is 0. So essentially there is no random intercept, but only an autoregression. So with an autoregression of 0.75, the correlation between the first and second time points is 0.75, and then it goes down, declines over time, and goes down towards 0 as the time increases. If you have a higher random, if you have a random intercept variance, then the correlation does not go down to 0, but goes down to the random intercept variance. This is all for a model which has the same unit variances for the observed variables. So the metric is easy to understand. Now, if you have a higher random intercept variance, the floor gets pushed up, and very high random intercept variance, there's not much change across time in the correlations because they're high throughout. On slide 10, we will then introduce dynamic models. And by dynamic models, I mean models where y is regressed onto itself. So like the univariate parts of the classic CLPM. So again, here we have the autoregression of lag 1. y1 influences y2, y2, y3. y3 is not influenced directly by y1, but only indirectly. This model is standard in time series models, for instance. Now, there has been efforts to add a random intercept to these kinds of dynamic models. So we have a dynamic random intercept AR1 model, which we're going to label D for dynamic RI AR1. And it has been discussed in the Boland-Brandt article from 2010. And again, you find that in the references. So it looks like this. You have the characteristic of regressions among the observed variables, although you have a random intercept as well. So the random intercept, so the correlation across time, or influence of I across time, goes through the y variables and through the, not only influences y1, but also y2 indirectly through y1 and directly. So it has a different structure altogether than the RI CLPM model. Now there's also a so-called ARMA version of this. All of this comes from the time series literature, and ARMA means AR, autoregressive moving average model. It has been discussed more recently in the Cipher and others articles in ORM. So the idea is that you have the model up here, but you add the fact that the residual of y1, or more easily seen here, the residual of y2 influences the observed variable at y3. So y3 is influenced by y2, the previous variable, the variable at the previous time point, and also by its residual. Very often that influence is negative, so that, for instance, if you have had a particularly high value on y2, on y at time point 2, that is the residual has contributed more here, then you will get a lower value of y3, so sort of going back towards the what it was at before. Okay, on slide 11 then, we are introducing in this paper, in this new paper, RI ARMA modeling. So here we're going to take the idea of a random intercept, no regressions among the observed variables, but regressions among latent underlying variables which have this moving average structure where the residual of F2 influences F3, while still having these zeros up here. as in the RI-CLPM. So this model is similar in spirit to RI-AR because of its separation of between and within individual variation, also referred to as latent centering, as we discussed, that is centering using the random intercept I. But it adds this MA component to the model. And that has proven in our investigations to be a useful addition, necessary addition to fit models well when you have many time points, when you get closer up to 10 time points. Perhaps you need it from, say, 7 through 10, whereas 3 to 6, you can 3 to 6 time points, you can fit the model well using RI-CLPM. For higher numbers, more time points, you may need this RI-ARMA model, which, as far as we know, is a new kind of model. And there is an equivalent measurement error version, just like it is for the RI-CLPM, and we call it RI-MEAR, where ME stands for measurement error. And that's actually a model that's more general than the TSE model, but just like TSE, it often presents estimation problems that you don't see with this RI-ARMA, RI-ARMA model. And we're going to try these models out in various applications. But let's just take finally here a look at the correlation structure for these ARMA models versus the AR models. And here, for simplicity, we have no random intercept, so the floor is 0 here in terms of correlation across long time spans. And the ARMA correlations are here at the top, whereas the AR correlations are at the bottom. So we see that the decline is, or can be, slower. The decline in correlation can be slower for ARMA models than for AR models. So if you let the R denote the lag 1 autocorrelation and B the MA coefficient, that is the coefficient for a residual at the previous time point influencing the outcome at the next time point, if the second autocorrelation is bigger than R square, then MB rather must be negative. And that's a picture we have here, a negative slower decay. If the second autocorrelation is smaller than R squared, which is the AR value, then B must be positive, faster decay. So that can happen as well, but in my experience, it's more seldom seen. Now this MI coefficient is often negative, so the correlation diminishes slowly over time, slowly than for the RI-AR model. So what you can do, if you like, in the real data, you can take a look at the correlation matrix, look down the first column, that is correlation between time point 1 and the rest of the time points, and the correlations typically decline. You can see how quickly they decline, or you can look at the last row and go from the last time point towards the first, seeing how it increases. And if you want to, you can compute the average correlation at different time differences and plot that average correlation. And that would be a counterpart to a plot of this kind, or the earlier plots that we showed. And you can then see if it looks like you have a very slow or faster decline, and you can look at what the floor is if it comes down towards 0, which indicates no random intercept, or if it comes down to a value higher than 0, where a random intercept is needed. Turning to slide 13, we'll take a look at new Mplus language introduced in version 8.7 for regular single level modeling. And we're listing here 5 ways to relate variables, some of which have been available before, but nevertheless for completeness. So we have 2 variables here. We can say that they covary using the with language, y1 with y2. But now what's new is that you can use this with for residual variables. So the residuals here for y1 and for y2 are going to be referred to as y1 hat and y2 hat, and we can have a covariance between them without having to introduce a latent variable. Now this all assumes that for this to be relevant, it assumes that these y variables are influenced by something else, such as a random intercept, so that you have true residuals. It should be a residual of a regression of some sort, even if it's a regression of a factor indicator on a factor. So that introduces the hat notation that has been available in time series analysis using DSIM and RDSIM. Actually RDSIM, but now it's available also in regular single level wide modeling. Now then we also have the on statement, of course, of the regular kind, and now we have the on statement of the y hat kind. So y2 hat, that's this variable, regressed on y1 hat with its residual. Again, assuming that y1 and y2 are influenced by some variable, so that these residuals are relevant, as can actually be seen as residuals. And the new, yet another new on feature is what we need for the moving average part of ARMA. That is, we have y2 regressed on the y1 residual, and then y2 has a residual on top of that. So that's y2 without a hat on y1 with a hat. So this residual language is for single level models and newly introduced in Mplus version 8.7. And the y hat notation is spoken as y hat, and as an example we have the RI-AR model, where we have autoregressions among the residuals from the regression of the y's on the random intercept. Now this residual modeling is available for both continuous and categorical outcomes, but not for nominal outcomes or counts or censored variables. Well, actually censored variables is available with WSMV, but that's a minor point. And for categorical variables, this is a real breakthrough. This residual modeling is done via the base estimator, and most efficiently by a base estimator. And that has to we had to develop a new algorithm for that, and Timur has done some ingenious work on that, and that is referred to in the overview paper that I referred to earlier, the new paper. So we can now do, therefore, RI CLPM for categorical outcomes, binary and ordinal. Now, to summarize this, in the continuous case, we have the 5 different ways to relate variables: 1, 2, 3, 4, 5, as we had on the previous page. So when we have 3 different estimators, and we just want to list what's available in which estimator. And for all 3 estimators, we can certainly say y1 with y2 here for continuous variables, and we can say y1 hat with y2 hat for all 3 estimators. And we can say y2 regressed on y1, of course, and y2 on y2 hat on y1 hat for all 3. And however, for the moving average situation, the y2 no hat on y1 hat, we only have that available for ML and WSMV, not yet for base, although it can be done using the equivalent mere measurement error formulation in the panel data case, although that can be a little harder to work with in terms of convergence for certain cases. Now if you turn to the categorical case instead on slide 15, there are a little bit more to say about that, and that will be covered more in detail in part 2 of Webtalk 4. The y1, y2 covariance is not available in maximum likelihood, as you may remember from Mplus use. There is no with statement available. Categorical variables calls for, with continuous latent variables, for instance, calls for numerical integration, and to get a residual covariance between 2 y variables, you have to introduce a factor. There's no with statement. Or you can use parameterization equals rescov. That can be used to allow for conditional non-independence, say in this factor analysis situation. But for the other estimators, we have y1 with y2 for both WSMV and for base. And footnote 2 says that here the latent y star variables are used. So it's not for the observed categorical variables, but for the continuous latent response variables y star, which is a natural way of describing association in the categorical case, both the binary and the ordinal case. For this residual covariance is also not available in maximum likelihood, like the regular covariance is not, but it is available in WSMV and base. For y2 regressed on y1, well, for ML, that means that we use the observed y variables. So it's the observed y1 that predicts the observed y2. Whereas for WSMV and for base, well, for WSMV, it is the latent y star variable that's the predictor here, not the observed. And for base, it is the, you have the choice actually. This y1 can be observed or latent, depending on how you specify predictor as observed or as latent. But for base, you don't have, for ML and for base, you do not have the moving average situation available to you. It could be developed for base, but it isn't there. But it is available for WSMV. Now, let's take a look at how this shows up, this new language shows up in two different situations. One is the growth model with autocorrelated residuals that we talked about in the growth modeling context. So we have a user's guide example 6.17, which looks like this. You have 4 variables and you have a linear growth model, I and S, with a linear development over time. And you have residual variances. And here we set them equal across time. And then we have these pairwise width statements for lag 1 and for lag 2 and for lag 3 here. These are the only cases with 4 variables. And then you have to add a model constraint. This is again in old Mplus, so to speak, where you introduce 3 parameters here as the 3 parameters here as functions only 2 parameters, residual variance, which is this equal residual variance, and correlation to power 1, 2, and 3. So this model specifies equality of autoregressions. The autoregression coefficients are equal across time, and the residual variances are equal across time. So it's a little complicated to specify, particularly if you have, say, 10 time points. Then you will have a lot of model constraints here. So in the new version 8.7 HATS language, here's how you specify it in the right column here. Same growth model, but then you just say, you refer to the residuals directly as variables. Y2 hat through Y4 hat is pairwise regressed on Y1 through Y3. So 2 on 1, 3 on 2, and 4 on 3. So directly relating the residuals to each other. And in this case, we have the perhaps more flexible model of free autoregressions. These are different coefficients. They're not the same across time, these autoregressions here. And the residual variances are free as well. If you want to mimic what we have on the left here, with equality of autoregressions and residual variances, you have to add special specifications on model constraints, using model constraints. So I'm not going to go through that. But this is a very simple specification, which will be useful. Now, we talked about several different panel data models here, and it's time to summarize them and show on one slide all of the different relevant models and look at how we refer to them. So we have dynamic models where y sub t is regressed on y sub t minus 1, previous time point. And we have non-dynamic models where we don't regress y onto itself. So among the dynamic models, we talked about autoregressive models. It's a classic model, which is dynamic by definition, y on y. Typical time series feature. And we have the ARMA model, which are autoregressive, moving average model. Classic model, which is dynamic by definition as well. And then we have the additions of the random intercept here, but a dynamic version of it. So the AR, autoregression, is of the classic dynamic kind, but with a random intercept added. And then same for ARMA, classic ARMA, dynamic but with RI added. And then we have the non-dynamic models. And again, the dynamic models are more like the classic CLPM, and the non-dynamic models are more like the RI CLPM. So we have the RI-AR model, specified for the residual within level latent variable centered part, and the RI-ARMA, which is ARMA specified for the residual within level latent variable modeling part. So these models are formulated for the univariate case. So you see how many models you can study in the univariate case, and then you pick the model for each process that you see as best fitting. That makes sense. And you put the two parts together, the two univariate parts together, into a bivariate model that has the cross-lags in it. So here's a second example then of how the new language plays out. Mplus input for RI-AR modeling, continuous univariate ML using the old approach versus the new approach in version 8.7. So old approach on the left and new on the right. So in the old approach, we specify all of these factors, all of these circles that we saw in the model figures, and we say that those residual variances are fixed at 0. So all of these factor loadings are fixed at 1 by default. And we define a random intercept factor I here. And then we do the AR regressions among the factors. So this is the univariate part of the RI CLPM. We add model equals no covariances to not have to fix at 0 all unwanted covariances, for instance, between I and the different Fs. On the right, you have the simplified language. No specification except for these two lines, really. And that's all you need to do for the univariate case. You have a random intercept and then AR1 regressions among the residuals. And then you can imagine then that going from this univariate case to the bivariate case will seem very simple to specify instead of having to add all of these factors by hand. On slide 19, we turn to analysis of data. And these data come from an article by Orth and others, 2020, given on the last page of the references. And the data set is called MWI and has to do with depression and self-esteem. It's detailed in the article. It concerns an adult sample, and it's 663 individuals and 5 time points measured 2 months apart. Now, the first thing you want to take a look at in your data analysis, apart from the distribution of each of the variables, you want to look at the coverage. That's important in the longitudinal setting. That is the proportion of the sample not missing for each variable in pairs of variables. So here you have this coverage table that Mplus gives you. So at the first time point, 99.4% had complete data, had data on variable S1, which is self-esteem at the first time point. And then you get this reduction, this attrition over time, reduction in sample size to a little bit over half remain at the last time point. Same thing for the depression, for the 5 depression variables, 99 down to 567. And what's also important here in these models, longitudinal models, is the joint coverage for adjacent pairs. You want these to be relatively high as well to be able to estimate relationships between adjacent time points. This data set looks fairly good, except for the attrition seems to be a little high here. The more attrition you have, the more your model estimation depends on model assumptions rather than the data. Turning to the analysis results, and I'm going to show you the Mplus scripts in a bit. We have then the univariate analysis of these data, and we're focusing on depression first for these 5 time points. And I list a set of models here, dynamic models and non-dynamic models. And I'm looking at the number of parameters, log likelihood, the BIC, and the MLR chi-square. I used the MLR to cover the fact that the variables are not normal. Nevertheless, they don't have any floor or ceiling effects, these variables. So MLR seems to be a suitable estimator, making chi-square more dependable and making the standard errors of the estimates more dependable. And then you have the root mean square error of approximation and the probability that that is less than 0.05, which you would like to have it. And then the usual CFI. So for the first model, that's the autoregressive dynamic model of lag 1, which is the univariate part of the classic CLPM cross-lag model. 14 parameters, here's log likelihood, here's the BIC. Chi-square with 6 degrees of freedom is much too high. The p-value is 0. You can't really blame that on a large sample size. Having an inflated, oversensitive chi-square, it should be quite dependable at sample sizes of around 600 or 700. So that 0 p-value staring at you should tell you that this is not the right model for the data. Don't interpret that model because it has rather little to do with the data. A root mean square error of approximation is too high, and the probability that it's less than 0.05 is 0. You can also get a confidence interval for this RMSEA from the Mplus output. The CFI tends to be over 0.9 for most any model. The baseline model is that all the variables are uncorrelated across time, and that's fairly unrealistic. So the model that has any correlation in it is likely to have a decent CFI. So I don't rely much on CFI in these model fitting studies. Now, adding a second lag of the autocorrelation here, that adds 3 parameters, and the log likelihood increases nicely, moves upwards, and the difference, 2 times the difference, is a chi-square test in itself, log likelihood ratio chi-square test with 3 degrees of freedom. You have 3 extra autocorrelation here in the AR2 model, and in AR1 model you have 3 autocorrelated with 1, time point 4 autocorrelated with 2, time point 5 or autocorrelated with 3. So clearly these extra autocorrelations are significant. And you see that also in the BIC, even though we increase the number of parameters, which BIC penalizes you for, you get a lower, that is better BIC, by the fact that the log likelihood improves so much. And so does chi-square. You lose 3 degrees of freedom because you have 3 more parameters, and chi-square is 13, so much better, but still not greater than 1% here. And the RMSEA, the probability that's less than 0.05 is not very high. Now going into the ARMA model, you add the moving average parameters, and there are 3 of those relative to the AR model. And you also see there a big drop in, or improvement rather, in the log likelihood. even bigger drop than adding a lag 2. And the BIC is therefore better. That also fits very well. I would say it's almost an overfit here, which often happens when you have only 5 time points. The ARMA type of models are more needed when T is higher than 5, closer to 10. And then you have the RI version of that, so that's a dynamic RI, AR1, sorry, not of that. This is the RI version of AR1 rather. So that adds one parameter, the random intercept variance, and that also gets a very good fit, almost too good to believe. Seems like you almost use too many parameters. If you do the ARMA model, adding the MA components, you have a chi-square with 1 degree of freedom that is 0. So that's clearly over-parameterized. You don't need 19 parameters here to do this model. And here you have the familiar RI-AR1 model with 15 parameters, which is 1 more than the AR model, the random intercept. And that random intercept improves the likelihood by a lot, as you see here. And again, you get a good BIC here, low BIC. It's actually the low, well, apart from this BIC, it's the lowest among them. And you get a good chi-square fit and a good RMSEA with a high p-value for being less than 0.05. And that model then, I bolded it together with the dynamic version of it, that is dynamic meaning you have regressions among the observed variables, whereas here you have regressions among the residuals or the latent variables rather than the observed. Those two models would be statistically indistinguishable, I would say. So you have to rely on substantive reasoning to determine which model you think is the best for the data according to your theories. The RI-ARMA model, again, looks over-parameterized. You don't need 18 parameters. I always get suspicious when the chi-square value is less than the degrees of freedom. Now that's depression. If you look then at self-esteem, the other variable in the pair, you have the same models here. You clearly reject the AR1 model, and it helps to include second order regression, but the p-value is not great, nor is the probability for the p-value for the RMSEA. If you go down to the DRI-AR model, that's a good fit and a good RMSEA. And likewise, the RI-AR1 is a good fit and not as high of a p-value, but high enough, I would say. So again, these two models, 4 and 6, compete with each other, and substantive considerations would have to be used to distinguish between them. And for the RI-ARMA model, 18 degrees of freedom, 1 more than the ARMA model, you actually have no solution here, which happens sometimes, or quite often actually, when you use more parameters than the data has information about. So that can exhibit itself in various kinds of error messages in the Mplus output. So now we're going to take a look at the Mplus outputs from the analyses of the 7 models on slide 21. And the first model is then an autoregressive AR1 model for self-esteem. So the use variable list works with S1 through S5, self-esteem at time point 1 through 5. And we're going to use the estimator MLR, and we will use starts equal 20 here, even though that may not be needed for such a simple model. And then the model, the essence of the model is here. S2 through S5 regressed on S1 through S4 pairwise. So S2 on S1 is the first autoregressive regression. Now, one little issue here is S1 itself. The way this statement is given, S1 will be treated as a covariate. It's not regressed on anything. And that would make for a likelihood that's based on S2 through S5 as dependent variables, which will not be then comparable to the other models. So just to get a comparable likelihood, we bring in S1 into the model here. So it is in essence a dependent variable as well in Mplus thinking. And it doesn't affect the estimates at all, bringing it in or not. It's just the likelihood metric would be comparable. And then we ask for modification indices here to see what's going to be needed in terms of adjustments. And then we have these different fit function values, and they're all the same here, showing that here we don't have any local maxima to worry about because it's a simple model. And this fit function values are in the ML, not the MLR scale. So you have to divide it by the chi-square scaling correction factor to get to the chi-square. So, but backing up, we have 14 parameters. Here's the log likelihood value that's recorded in the table. Here is the BIC value that's recorded, and then the chi-square 6 degrees of freedom equal to 104. So it's this scaling correction factor that we divide the fit function value with to get to the 104. Now, looking at the estimates here then, we see that we have positive and fairly large autoregressive coefficients. We can look at them in the standardized SDYX scale as well, and they are large there as well. And now we want to take a look in this case at the modification indices, and particularly the on statements here. We see that we have some fairly large ones here, and some of them are interpretable and some are not. We have, for instance, S3 on S1 has a large modification index, so the chi-square would improve quite a lot if we free that. And that's saying then that we have an autoregression of order 2, S3 on S1, and same thing for S4 on S2. So that suggests an AR2 model, and that's the model that we're going to turn to next. And then we turn to model 2, the AR2 model for self-esteem. So that's simply adding the second order autoregressions on this line, S3 on S1, S4 on S3, S4 on S2, and S5 on S3, so a distance of 2. So just adding that, we then find a much better, still fairly stable model. We have no replications, no different starting points giving different likelihood values or chi-square values, and we have a much better fit. P-values inching up a little bit. And we see then that the second order regressions, S3 on S1 is the first one, is significant and fairly large still. Same thing for S4 on S2 and S5 on S3. Turning then to model 3, the ARMA 11 model, we have the regular autoregressions of order 1, lag 1, and to this we now add the moving average component. So that's this line in the input for the model. S3 on S2 hat, the residual at the previous time point, and S4 on S3 hat, and S5 on S4 hat. Note that we don't add S2 on S1 hat, because the residual S1 hat is the same as S1 in this case, because S1 is not regressed on anything. As we will see later when we have a random intercept, it will be regressed on something. But here S1 and S1 hat are one and the same. So if we started at S2 on S1 hat, we would get a non-identified model. And in this case, let's see how stable the fit function is, the likelihood essentially. Same value for all of these starts. So it's a parsimonious model, and one that's easy to fit, and it gets quite a good chi-square, as we talked about slide 21. And now we turn to model 4, which is DRI AR1. So here we have a random intercept, the RI, but we do it in the dynamic sense. So adding the prefix D, because the Y variables or the dependent variables are going to be regressed on each other. So here's the model then. IS, the intercept for self-esteem, defined this way in a by statement with fixed loadings 1. And then we have S2 through S5 pairwise regressed on S1 through S4. So this is then a simple to set up model, and it, as we saw on slide 21, is quite competitive with the more commonly used RI-AR1 model. And we can look at its stability here. It's fairly stable. It's a very parsimonious model with only 15 parameters, so it shouldn't have any problems. And we get this fairly good or very good chi-square value. Turning to model 5 on slide 21, we are looking at the DRI ARMA model. So we have a dynamic model, so regressions among the observed variables, and we have a random intercept, and we have auto regressions and moving average going on at the same time. So the random intercept is specified as usual, and the auto regressions of order 1, lag 1, are specified as usual. And then we have the moving average part, where S2 is regressed on S1 hat, the residual at the previous time point, etc., up to S5 regressed on S4 hat. So here you notice that we start at S2, not S3, as we did for the ARMA model. So here we have the S1 variable is now a dependent variable thanks to the random intercept. Therefore, there is a difference between S1 and S1 hat. So we don't have that identification problem that we had before. And that's because of the introduction of the random intercept. So now we turn to model 6, RI-AR1 for self-esteem. So this is the univariate part of the popular RI-CLPM model with lag 1. So we define a random intercept factor as before, and then we define the residuals in the regression of the S on I. They are then regressed. They have an autocorrelation of order 1, S2 hat on S1 hat, etc. Without having to specify these factors, without using by statements, we get this automatically done. So let's take a look at the results here. have a stable model, 15 parameters, good chi-square. It's a good model. And let's take a look at the results here. So here we have the auto regressions on the within level, so to speak. This is within person regressions. That is having residualized it or latent variable centered it by the random intercept. And we see then actually that only one of the autoregressions is significant, S4 hat on S3 hat. The other ones are even negative, but certainly insignificant, so we can ignore that. This is pretty much 0. Oh, here we have a second one, yes. Two significant effects. And what do they look like in a standardized scale? The two significant ones are 0.43 and 0.53. And we can also take a look at, while we're at it, the variance for the random intercept. We want that to be substantial to see if there really is a latent trait influencing the outcomes at all time points. So 0.299, so that's like 0.3, and a fairly small standard error, meaning that that variance is substantial and it makes sense to introduce a random intercept. Now we can also take a look at the R-square values here. It's a little bit of a new issue here. So we have R-square for the observed variables S1 through S5. That's the variance explained in those variables as a function of the random intercept. So it's a fairly high variance explained here, 7.8. But then we also have R-square for the latent variables, the residuals in the regression of S on I. S1 is not regressed on anything. S1 hat is not, but S2 hat, of course, is regressed on S1 hat. So here we have an R-square. It's very small because we saw that those coefficients were fairly small. And we only get something of interest for S4 and S5 where we had significant AR coefficients. So those are the R-squares in the regression of the residuals among themselves. So two kinds of R-squares. Now we turn to the final model on slide 21, model 7, the RI-ARMA model. So here we have a bit more of a complex setup. We have a random intercept and we introduce factors behind each of the observed variables with the residual variances 0. So that's like the old way of doing RI CLPM, introducing a factor. And we have to have deviate from the default by fixing the covariance between the random intercept and the first factor to 0. You can also use model no-cov if you want to. And then we have auto regressions of order 1 among the factors, so the residualized versions onto themselves. And then we have the moving average part here, which is FS3 P on FS2 hat through FS4 hat. So that's how you specify this model. You could have done it by having a double hat style, but we'll see if how much this model catches on, and maybe then we'll make the language more convenient. Here again we start the regression at number 3 because of FS1 and FS1 hat being one and the same variable here. So let's take a look at that. We see the fit function values, and we did 100 starts here to be sure, and we see that we have close values here: 3.03, 3.04, 3.044, 48, that's 3.06. So a lot of close local maxima, which indicates an unstable model, and 82 starting values didn't even converge. So this sort of are indications that we're over parameterizing. Too many parameters. We can't extract that much information from the data for the parameters of this model. And then we get this standard error warning that the model may not be identified, parameter fs4 hat, and the condition number is very low, 10 to the minus 11. So we're close to it not being identified empirically. So we can also take a look at what the estimates are here, and where the optimization stopped, and we see fs2 hat, that the variance of that residual is actually negative. Once again, indicating that the model is too complex, we can't get a solution, the condition number is too low, and the solution is not interpretable or not giving admissible estimates anyway. Turning to slide 22, we'll look at another data set from the National Longitudinal Study of Youth 79, endless Y79, where again we'll look at depression and self-esteem. And this is again data taken from the Ort et al. Article, and it concerns adolescents and young adults. Total sample size 8,000 plus, and total number of time points is 11. These are measured 2 years apart from 1994 to 2014. However, we don't have 11 time points for any one person. The maximum is more like 7 and a smattering of people with 8 time points. So there's a lot of missing data, perhaps some of it by design, I'm not sure. So with this large amount of missing data, you will have to use analysis option coverage equals 0 to get past Mplus default of stopping you at coverage lower than 0.10. And you have to use many starts, 20, 50, and maybe even 100. But at the same time, be aware that when you have this much missing data, model assumptions, as it says, are given too much weight relative to data. And the coverage is especially poor for self-esteem, the 11 variables designated by or denoted Y here. And you have these off-diagonal 0 coverage, so nobody has information on both the 3rd and the 4th time point. Nobody on the 4th and the 5th time point. And even worse here, 3 zeros in a row. Now it is possible to estimate, these off-diagonal elements particularly influence the estimation of autoregressive features. 3 on, or 4 on, 5 on 4, and 4 on 3. You have to borrow information further away at lag 2 to be able to infer what the lag 1 estimates would be here. And that gets too difficult for the optimization machinery when you have 3 zeros in a row here. Here we have only 2. For depression, the missing data situation is a little bit better for some reason, and we're able to do analyses of depression univariate without imposing invariance across time. I should mention that that is one way of getting past this. If you hold autoregressions invariant across time, then you have more stable estimation, because then you borrow from the off-diagonal elements that are not 0. And that's actually how the Ort article gets by this problem when they do a bivariate analysis of self-esteem with depression. Turning then to the univariate analysis results, we look at the AR1 model, which is the model that Oort settled on, although with the assumption of invariance, a stricter model. So you see there that we have a fairly poor chi-square. Here, to some extent, since you have over 8,000 individuals, you may blame that on chi-square becoming oversensitive with large n, although at a certain time point you don't have all 8,000. I haven't looked at the details of how many observations you have per time point in this case. Probably far less than 8,200. But anyway, for these data, you may want to also rely more heavily on RMSEA, the approximate fit. But even by that measure, probability p-value is 0 that you have an RMSEA less than 0.05, which is desirable. And then even the CFI is poor. AR2 seems to work a lot better. You get a strong improvement in the log likelihood, and look at the chi-square. It drops down quite a lot. And now you have an acceptable RMSEA with p-value 1 here. Now, ARMA 1.1 then is a model that I boldfaced here, so it means I found that to be a good one. Note that that has the same number of parameters as AR2, but look at the chi-square. So much better. So same degrees of freedom, but 43 instead of 456. So on the one hand, you can say that this model may be, AR2 model may be acceptable because of large sample size and the RMSEA being okay, but if you have a competing model, you can really see, with the same number of parameters, you can really see that you haven't looked at your data thoroughly enough if you stop at the AR2. The ARMA model, certainly for the same number of parameters, is much better. And if you go then further down, the dynamic random intercept models don't get that great of chi-square. Well, the AR2 does maybe, but the dynamic RI ARMA model, when I say 1.1, that means order regression of order 1 and moving average of order 1. 3247, that looks like a good fit. But of course you have to get up to 43 parameters, whereas you got a just as good of a fit with only 41 parameters here using the ARMA 11 model. And we're going to take a look at that model. Trying to include auto regression order 2, which works so well in the AR2 model, gives you no solutions, just too many parameters for that. The RI-AR1 model, which is the basis for the RI-CLPM model, doesn't do too well here with chi-square, but it's all right by RMSEA, but we have already seen that we get a better model if we go to ARMA. True, we have to add more parameters, we go from 33 to 41, but still I would tend to choose that, the model 3 instead of model 8. Adding a second order auto regression gives you too complex of a model. When you have that second order auto regression in these more complex models, you easily overtax the optimization because of all the missing data in these in this particular application. And then finally you have the ARMA model, which gets a good chi-square and a good RMSEA, 42 parameters and 3340. It has one more parameter than the ARMA model, and similar degrees of freedom, similar chi-square, similar p-value. So model 3 and model 10 are competitors here, but let's see which one is actually looking better in terms of the Mplus runs. So let's take a look at that. So here we have output for the ARMA 11 run. So that is first order auto regression, and then the moving average model where we start at the third time point, because otherwise Z2 on Z1 hat would be the same as Z2 on Z1. because they are not dependent variables. Again, we add z1 to get the likelihood in the same metric. Anyway, so this model then, 50 starting values, 49 did not converge. So you may want to use 100. Starts equals 100 here, but at least those two show replication of the best log likelihood. This is in the scale of the log likelihood, taking the scaling correction factor into account. Now we can take a look at the estimates here, and you see that the moving average parameters are negative indeed. So a high residual at a previous time point tends to give a lower value of the outcome at the next time point. So that's often seen in data, and that's the feature that makes the decay of the correlations across time be slower than for the regular AR model. So now let's take a look finally then at the model for ARMA, which seemed promising, good chi-square, and we use 100 starts here in addition to the coverage equals 0. 100 starts, and we look then at quite a few relatively close likelihood values, which means that the likelihood, again, cannot distinguish very well between different kinds of solutions. That says you don't have enough data, don't have enough information in the data to determine all of the model parameters. But anyway, the best solution is replicated, but we get this message. Standard errors are not trustworthy due to non-positive definite first-order derivative matrix. And that's the matrix that is used for standard errors when you use the so-called MLF, as in Frank estimator. So you have a very low condition number, which says that the model is teetering on not being identified. And FT hat, let's see, what do we have here? All of them are positive, the variances, but nevertheless, it's not quite a trustworthy solution. So let's take a look at the actually running it by MLF. This is an interesting trick that TMR taught me, that you run it with the MLF estimator, and then that low condition number gets reflected in the standard errors. So you see then standard errors here being quite large, not for all parameters, but down here, look at 48 for F6 on F5 hat, the MA moving average component. Same thing for F7, for F8 and F9. Those large standard errors is an indication that you get, when you have an infinite standard error, it means the model is not identified. This one is on its way to becoming not identified. So not a great model after all. So in this case, we probably would choose model 3, ARMA 11, with its 41 parameters. So that's neither, it doesn't have a random intercept component, and it seems to be a simple model that seems to be better for these data. I would say though that if you had t equal 11 with everybody or many people or most people having all 11 time points, I would bet that the model 10 ARMA model would win and would be the best model. But here, thanks to so much missing data, we have to settle for a simpler model than that. On slide 24, we turn to bivariate analysis. And the first model we show here is the random intercept cross-lag panel model. And it's shown in two different versions. On the left it's portrayed in the way it has been set up traditionally in programs like Mplus. That is, we introduce these factors to capture within person variation, so variation across time, free of the random intercept influence. The random intercept influence is the observed variable, and the observed variable is also influenced by the within part. So you have the between part and the within part. And that's the old approach, using factors to explicitly create a factor variable representing the residual going into y1, because the measurement error is 0 up here. On the right, we have the new approach using hats, so we don't create any latent variables, and they are created automatically inside of Mplus, and that particularly benefits Bayesian analysis, which is the primary estimation technique when we turn to categorical outcomes. So here we don't have to draw circles. You can if you want to, or maybe small circles, but no circles at all seems to be just fine. So we have these cross-lagged effects among the residuals, and with the covariance between them for all time points. A little bit simpler drawing. Now, turning to the RI-ARMA model, which is the new model that we've introduced in this paper, which is suitable for a longer time series. Probably you need at least 8 time points. You have the same situation as in the traditional way of representing the residuals, namely by factors. In this case, we don't have access to the y hat, the hat notation. It would actually require a double hat, if anything. So we have to define these latent variables again, with measurement error 0. Because we want to be able to regress, say, take the third time point here, we want to be able to regress y on z and z on y, but we also want to be able to work with the residuals, namely the residual of fy2 influencing fy3. That's this path here is the moving average part, the residual at an early time point influencing the variable at the later time point. And same thing for the z part, that is influenced by the residual of fz2. And these residuals have correlation between the two processes across time. And once again, we don't include a moving average part from the first time point, but only from the second. Now, this is a simple version of representing the RI-ARMA. The fuller version, which is also discussed in the paper, is when these MA components also have cross-lagged relationships. For instance, the fy3 component here could be this residual could be regressed on the residual at the previous time points. So you have these cross effects between the residuals as well as between the variables themselves. But that is a more complex model with more parameters, and would then require more time points. So this is a parsimonious model that may be sufficient. Now, turning then to slide 26, we take a look at the results for the bivariate analysis of this data set of depression and self-esteem, 5 time points, sample size 663, that we did the univariate analyses for. And on the left here, you have the whole sequence of models in a similar notation from the univariate analysis. Although in the univariate analysis, instead of using the word CLPM1, we use AR, order regression 1, lag 1, and order regression lag 2. Similarly, I used RI-AR1 for the univariate analysis, but here now we're doing a bivariate analysis. So if you like, you could just add CLPM at the end. So RI-AR1 CLPM, or RI-CLPM1. But so it should be understood that all of these models are CLPM, that is cross-lag panel models, I just didn't want to tack on the CLPM suffix for all of these acronyms to make them that much longer, and I wanted them to be similar to the univariate slides. So I start with the model 0 here, where you have the cross-lag panel model with the lag 1, so it's an AR1 model for each of the two processes. And the invariance refers to the autoregressive parts and the cross-lags, not the residual variances or covariances. And this is the model used in Ort's paper. And it has 29 parameters here, and the MLR chi-square with 36 degrees of freedom is 207. So a clear rejection of that model. It's not a model that fits the data well. The root mean square error is too high, and you have probability 0 that it is less than 0.05. So we would reject that model and not interpret it because it's not close enough to data. This model, CLPM1, allows for time-varying auto-regressions and cross-lags. And it looks like we reduced the chi-square a little bit, but we also reduced the degrees of freedom because we've gone from 29 to 41 parameters. This model is also, in my view, clearly rejected. And although the RMSEA seems to obtain a good value. But I would say we can rely on chi-square here, and this is not a well-fitting model. We could add a lag 2 for each process. And in fact, we should mention that the two processes don't have to have the same lag. In fact, they don't have to have the same model. You could have, for instance, a CLPM or AR1 process for one, AR1 model rather for one process, and an RI AR1 model for another, for instance. I'm not saying it makes sense, but we don't have to have the same models. But we're going to entertain only models that are the same for the two processes. So adding a lag 2 certainly improves chi-square quite a lot. We get a non-zero value in the p-value here. And of course, you can take the difference here between the two models with 6 degrees of freedom. You can create a likelihood ratio chi-square test, 2 times the difference here, which is hugely significant, pointing to lag 2 as being the better model. However, we can get better fitting models with lag 1 if we go down here in further modeling. We have the ARMA model, auto regression of order 1 and moving average terms of order 1. And that's a model that fits quite well. Now it has 50 parameters, so it has more parameters than the CLPM2, but it fits very well with all measures, according to all measures. Now the dynamic RI AR1 with 44 degrees of freedom, so 44 parameters, fits well as well. So you have a p-value of 0.05 plus here. So that is a dynamic model like the previous ones. And you have the dynamic ARMA model as well here, which goes up to 52 parameters and fits well as well. So those are the dynamic models, and among the dynamic models you have the best big for, let's see, 3349 for this dynamic RI-AR1. But the ARMA model is not bad either. Now turning to the non-dynamic models, we have our RI-AR1, which is the same thing as an RI-CLPM with lag 1, the standard RI-CLPM. And that one fits quite well. 21 degrees of freedom, 34, very similar to the to model 4, 21 with 33, basically indistinguishable models. So there you have a choice in terms of substantive theory. Which model is it that you think makes more sense from a substantive point of view? Statistically, they are essentially indistinguishable. Now you could go to the RI-ARMA model as well, although we have only 5 time points here. So it is really too few time points to work with this model, which has 50 parameters. So you get a chi-square 15 that's 9, and as I said, I'm always suspicious of models that have lower chi-square value than the degrees of freedom. It seems like overfitting. It has too many parameters, but it is possible to analyze it that way. So there you have a set of models. If you're interested in random intercept models, which I think is a good idea, you have the RIAR1 or the dynamic RIAR1, depending on whether you want relationships between the residuals over time or between the variables themselves over time. Two different substantive interpretations. With more time points, it's possible that we can tell them apart, but not with 5 time points. I should also mention that in some writings for the dynamic RIAR1, like Bolen and Brandt and Cypher, it's recommended that you free the first loading of the random intercept factors from a substantive point of view, or from a modeling point of view. The first time point is different than the others because it's not influenced by anything previous. So, and when you do that, in this case, you don't get much of a difference. You may in other situations, but not here. So then let's take a look at Mplus outputs here and go through different models and discuss them. So let's now turn to the Mplus script for the bivariate analysis. And I'm going to refer to the model names that we use on slide 26, where we summarized the fit to the data. So the first model is what I call model 0 on slide 26, the classic cross-lag panel model without any random intercept and with the addition of time invariance for the auto regressions and the cross-lags. So this is the model used by Oort in his paper. So on the use variable list, you have both the S variables, self-esteem, and the D variables, the depression variables. For safety's sake, we allow starts 20 different starting points, although that should not be needed for such a simple model here. And then you specify the model such that you separate the auto regressions for the S variable and for the D variable, and the cross lags for each of the two variables, and holding them equal across time. So instead of having 4 separate parameters here, 2, 3, 4, 5, that's 4 parameters, that auto regression is held equal in, so 1 parameter here, 1 parameter for the depression auto regression, and then 4 cross lags for S on D and 4 for D on S are each summarized into 1 single parameter. So in that case, then we get the chi-square here. First of all, fit function values show that there's no problem finding this solution. There's no ambivalence here about what the best solution is. And we get the chi-square value of 207 with 36 degrees of freedom. So we reject that model. But that's the model that Oort reports, and he finds then that S on D, which is held invariant, is negative and significant. Same, minus 0.12 throughout. And it so happens that D on S is also minus 0.12, significant. It's not held equal, it's just an unpedagogical outcome here. You can see from the standard errors that they're different, and from the z-scores. But anyway, both of them are negative, which is what the authors expected. High self-esteem lowers depression next time. High depression lowers the self-esteem the next time. And you can look at the standardized results here, SCDYX standardization, and you get, I think what he reports in his article, minus 0.08 and minus approximately 18. Even if you hold time invariance of the raw coefficients, the standardized coefficient is going to be a little bit different because of the residual variances being different across time. Now let's then turn to the next model, and RIAR1, so that's model 6. So you may want to call it RI-CLPM. That's the standard Hamaker et al. Model. And we then see that the specification is now in a more compact fashion because we don't have to hold any time invariance. So in addition to the random intercept factors here, we have S and D regressed on S and D. So S on S and D on D. It's a compact way of writing the autoregression. And the autoregression is for the hat variables, that is the residuals in the regression of the S and D variables on their respective random intercept. And then this line here, second line, gives the cross lags, S on D and D on S in a compact fashion. And then you have the p-width, pairwise width variables. And that gives you a list of solutions that are all the same, which indicates that you have an easily found maximum likelihood solution. So the parameter estimates are easily determined from the information in the data. And you have chi-square of 34 with 21 degrees of freedom, which is what we reported. So that's a well-fitting model. And it has 44 parameters instead of 29 for the invariant cross-lag panel model and 41 for the non-invariant. Although you need it with CLPM, you need lag 2, which has 47 parameters, not far from the, well, it's actually more than the model we're looking at. So 47, the classic cross-lag model needs lag 2 with 47 parameters, whereas this model we're looking at now has only 44 and has a better fit. So it's just the right kind of model. So what are the estimates here then? Well, if you look at them here, S on D, that's negative, but it's insignificant for the second on the first time point. Third regressed on the second, negative but insignificant. Fourth regressed on the third, negative, and there you have a significance. That's the first one, S4 on D3. And it's the only one of the S regressions that's significant. Cross-lag with S as dependent variable, only at between time point 4 and 3 do we have significance. For the D variable as a dependent variable, D on S, positive significant. That's not what we expect, but this is the result we get from a better fitting model. D on S at the next time point, insignificant, essentially 0. D4 on S3, insignificant. D5 on S4, that's the only one then that has a strong negative significant effect. So there's a different outcome, and then you may want to start thinking about why does this happen in these real data? What are the issues here that cause these unexpected directions and of influence and only significant influence at certain time points? Maybe you have to bring in time varying covariates into this model. And what are the effects in the standardized metric? If you just look at the significant ones, minus 0.31, that's substantial. And for the D, plus 0.21, also substantial, and minus 0.30. In any case, those model results contradict those from the CLPM model, and you would tend to put more faith into the results of this analysis because it fits the data better. It's closer to the data. So finally then, if we look at model 7, the RI-ARMA model, which really is a little over-parameterized for only five time points, but we want to show what it looks like. So here you probably need starts equals 20, perhaps 50, perhaps 100. So what you do here is you revert back to the old way of specifying RI CLPM models, namely introduce a factor behind each observed variable with residual variance is 0, as in the classic way of portraying the Hamaker et al. CLPM, RI CLPM model. And here you have to set some unwanted covariances to 0 between factors. You can have model equals no cov as well. That would work fine. Then you wouldn't have to say that. And then you specify in this compact form the factor for S, regressed on the factor for S. That's the order regression of order 1. Same for the D on D. And here are the cross-lags. Sorry, not the cross-lags, but the MA, the moving average component, FS3 to 5 on FS2 to FS4, deleting the first time point, regressing on the first time point for reasons we discussed in the univariate case. And then the MA part for the D part of the model, same way. Using the hat language here, but now it's hats for factors, not for the variables. So here you have the cross-lags, S on D, D on S. And then you have the p-width statements. And that gives you the, well, let's see first. Here we have, here you actually see that you have a couple of different solutions, 12 and 17. So this is a bad solution we got. And 17 starting value runs did not even converge. So here you see that the model is difficult. The likelihood, one could say, is doesn't have a well-defined maximum, global maximum. So you may want to, but it could be quite bumpy. So hard to tease out all this information from the data for all the parameters in this model. We even want to run it with 50 starts or even 100. I think I did that and found no difference. That is the best solution at the top there. But we have some comments here on problems for the model. And we're just going to take a look at the, let's say, see if the residuals, well, we have a negative residual here. So it seems like it's not the right model. Now, what about the on statements? I don't know how much credence we will give to them, but we have insignificant F on S on D, significant S, insignificant S on D still, positive but insignificant, insignificant, insignificant. So none of the S regressed on F, sorry, S regressed on D are significant. But let's see, and we have only one D regressed on S significant. So in that sense, to some extent, the RI-ARMA model and the RI-AR model agree. And there isn't uniform cross-lagged effects across time, and therefore the invariance model is not appropriate. Turning to slide 28, we're going to take a closer look at the testing of time invariance for the auto regressions and the cross-lagged effects. And we stay with this example with 5 time points for depression and self-esteem. And we can do that either by running the two models and doing a chi-square difference test. Since we're using MLR, we have to use those special computations that we show on the Mplus website. And perhaps it's easier to do it in the following way, which doesn't require 2 runs. And it's probably pretty much the same results. So we're going to use the wall chi-square test, model test with MLR. And first let me show you or tell you about the results, and then we can take a look at how we did it. So for the cross-lag panel model with auto regression lag 1, we can actually not reject invariance across time. And with cross-lag panel model order 2, we can reject, but not very strongly so. So this is a little interesting phenomenon that happens. If you go back to slide 26, you see that we're looking at comparison between the invariant model and the cross-lagged free model, free autoregressions and cross-lags. Neither model fits well. Both models fit poorly. And the chi-square difference test is not designed to work well in that connection. So I would say that this is a false result that we should not rely on, because the two models, neither model fits well. So it doesn't matter that the invariance test can't reject invariance. If we look at the other models that have the random intercept in it, we see a clear rejection of invariance across time. So here it's clear that we should work with a model that we looked at before with varying autoregressions and cross-lags. You clearly reject invariance across time, and also for RI ARMA. So it's interesting that CLPM1 model is rejected not only in its non-invariant case, or rather it's rejected not only in the invariant case that Ort presents in the paper, but also in the non-invariant case. And even the CLPM2 model would be rejected. Although once again, since you don't have great fit for it, even in that case, for the cross-lag, for the order 2 model, I would say that the results may not be that trustworthy. But here we have neighboring models that are, at least one of them fits well, so we can rely on those difference testing. So time invariance is rejected. So how do we do it? Well, here's what you have on slide 29. We do it for the CLPM1 model. So you have this compact way of writing it. You may prefer to write it out S by itself and D by itself, but here it's in compact way. So we have 4 S on S and 4 D on D. So we have a total of 8 autoregressions. So we just list them as the free parameters they are. Same thing for the cross-lags, 4 plus 4. And then in model tests, since we're given those parameter labels, we can use model tests to relate the second autoregression to the first, the third to the first, the fourth to the first. That's for the S variable, self-esteem. And there are 4 parameters, so there are 3 comparisons to the first. You should not have 4 comparisons, you should have 3. Same thing for D, that starts with A6 compared to A5, 7 to 5, 8 to 5. And then you have the cross-lags for S on D. You take the first 4 with a comparison to the first, and then for D on S you take the last 4 with comparison to the first for them, which is C5. And out comes the test of the wall test with degrees of freedom 12 and the value 15 and a p-value. And again, we cannot reject invariance in this model, but that is due to both models being far from the true model. So on slide 30 then, to conclude from these data analysis, so this is limited to the depression and self-esteem analysis for the T=5 MWI data from Ort's article, and the depression analysis from the NLSY data of Ort. And we conclude that CLPM tends to not fit the data well, which is expected from statistical considerations. It is a model that does not recognize the hierarchical multi-level nature of the data. That is, you have time within individual. It's a 2-level situation, and in any 2-level model you should at least include a random intercept, if not also a random slope. The random intercept is really needed to capture the main correlation across time. There may be further correlation by autoregressions among the residuals, but the major correlation is likely, or a major part of the correlation is likely to come from the random intercept, which in psychological texts would be referred to as the trait, the stable component, varying across individuals but not varying across time. A better model is one that includes a random intercept. A random intercept cross-lag panel modeling, that's the Hamaker et al. Model, needs at least 3 time points or more than 2, and it tends to fit the data well when the number of time points is between 2 and 7. So 3 up to 6 tends to fit rather well. But RI-ARMA tends to be needed when you go above 6. And that's what we have seen in several data sets. And note that univariate RI-ARMA, you need to have more than 4, at least 5 time points for it to even be identified. In the univariate case. In the bivariate case, you don't need to have that many. Or you get an over-identified model when you have t equals 5. Now the dynamic alternatives of ARMA and I should say D, dynamic RI-ARMA, are also good for a larger number of time points, as we have seen for these data. And the choice between them and RI-ARMA should be based on substantive considerations. Further considerations then on slide 31. If you are concerned about confidence intervals, the usual symmetric confidence intervals that we get, in maximum likelihood, the estimate plus minus 1.96 times the standard error, that symmetric confidence interval may not be the right kind of interval in all cases. For non-symmetric intervals, which are more general, you can either then do bootstrapping, or you just do a Bayesian analysis which directly allows you non-symmetric intervals for the posterior parameter distribution. And I would also urge Monte Carlo simulations, particularly for these new models, where you get a feeling for how well you can recover the parameter estimates and the standard errors, varying the number of people, the number of time points, and the effect sizes. And you also thereby can get a feeling for the power that you have to reject that the cross-lagged effects are 0. Now some models, random intercept is not sufficient, but you may need to add a random slope or a quadratic slope. But that can result in, if you combine that with a structure for the residuals within cross-lagged effects, you may get no solutions or inadmissible solutions unless t is large, much larger than what we typically see, around t equals 3, 4, 5. Now you can also view these models, some of these models, as measurement error models, and you can parameterize them using the trait state error model or the measurement error AR model. And we discussed that in the paper, and it is, however, a more fragile type of parameterization that can easily result in no solution or in inadmissible solutions. And a future aspect of these kinds of analysis, I think, is the causal inference, causal analysis, whereby potential outcomes reasoning and causal effect reasoning, you may want to use other estimation techniques to estimate the cross-lagged effects and try to take into account in a more robust way unobserved time-varying confounders. On the last 2 slides, where I give you a bunch of references, some of which I haven't mentioned at all, but there are some good articles here. For instance, Boland and Brandt is a nice one. And here we have a FAQ on Hammaker Mulder's website, a beginning of a response to the ORT article criticizing the use of the CLPM. And we have Usami, who has, towards the end of this 2021 article, which you point down here, has some reasoning about causal inference. So with that, I'll end Webtalk 4, Part 1 for continuous variables.